Imagine you're baking a cake and the recipe simply says bake at 350. It doesn't mention anything about the units, whether it's degree Celsius, Kelvin, or degree Fahrenheit. Confusing, right? Use the wrong one and you might end up making a burnt mess instead of a delicious cake. Well, any quantitative observation or measurement, like temperature here, has to be represented by a number followed by a unit, right? Now, which unit to choose? For example, India can use a unit of temperature as degree Celsius and America can use degree Fahrenheit. What's a big deal about it? Well, there is a big deal about it. Let me tell you one of the most famous and costly examples of what can go wrong without proper unit standardization. NASA launched the Mars Climate Orbiter in 1998 to study Mars atmosphere and climate. The spacecraft was built and operated by NASA's Jet Propulsion Laboratory, commonly called JPL, and Lockheed Martin. Well, in September 1999, the orbiter entered Mars' atmosphere at the wrong angle. It got burnt up and it was completely lost. What do you think went wrong? Well, it was not a technical failure or a software bug. It was a unit mismatch. What happened was, Lockheed Martin used one type of a measuring system, whereas NASA JPL used the SI unit system. Well, there are many different systems of measurement. We don't have to get into this US customary unit system right now, but all that we need to understand is there was a unit mismatch that led to the loss of millions of dollars. Years of research got wasted and we got nothing in return. Sheer wastage of time, money, and resources because of a silly error, that is, a failure of consistent standard units. Hence comes the International System of Units, abbreviated as SI units. So standardized units act as a universal language across the world. Now this SI system is quite sorted. The SI system has 7 base units. Alright, these units are for the 7 fundamental scientific quantities. Now, before we get into the units of these fundamental quantities, let's understand the term fundamental. What are the fundamental scientific quantities? Well, the basic physical quantities that cannot be broken down or derived from other quantities are fundamental scientific quantities. You may imagine fundamental scientific quantities as individual Lego pieces. Just like you can snap 2 Lego pieces together, derived units are formed by combining 2 or more fundamental units. So all other quantities in science like speed, force, energy, pressure are derived by combining these fundamental quantities. Well, let's dive into each of these fundamental units. Let's begin with the most intuitive and visible quantity. The physical quantity which helps us know our height or how far the moon is, whether you're building a table or launching a rocket. It all begins with length. Well, length helps us in measuring the distance. Whether you're finding distance between 2 objects or finding the diameter of a rod or simply calculating the depth or height. The units which are the SI units are in meter. So we write it as small m. This is the symbol of the SI unit. Now the common instruments that can be used are ruler, vernier caliper, measuring tape for finding out the length. Next is the mass. Mass measures the amount of matter and the SI unit of mass is kilogram, which we write like this, small k, small g. We have different instruments to measure mass like digital, scale, analytical, balance, etc. Now it is time to talk about time. Well, time is a quantity which helps us in measuring the duration, right? The SI unit of time is second, which we write as small s. The different instruments that can be used are stopwatch, wristwatch, etc. Now next is the temperature. And what does temperature measure? It measures a degree of hotness or coldness. The SI unit is Kelvin and the symbol is capital K. I know, we use degrees Celsius here in India, and if you were in US, you would commonly use degree Fahrenheit. But yes, the actual SI unit of temperature is Kelvin, all right? The common instrument that we know we use is thermometer. Next is now electric current. The electric current is nothing but actually the flow of electric charge. So electric current can be measured in ampere. The symbol is capital A, and the common instrument that we use to measure electric current is ammeter. Now the next one might be new to you. It is luminous intensity, which actually measures the brightness of light. That's right. We can actually measure how bright the light is. The SI unit is candela and the symbol is small c small d, not capital C capital D, but small c small d. And the common instrument that we use is photometer. Like the name suggests, photo is for light. So a meter that is used to measure the light, the brightness of light is photometer. Now, the next one is chemist's favorite. It is the amount of substance. So if we want to calculate the number of particles, maybe the number of atoms, number of molecules, we can measure it in mole. The SI unit is mole, M-O-L-E, and this is the symbol of mole, M-O-L, all in small, M-O-L. And this is the unit which is going to be the star of the chapter. So how to calculate it? There is no instrument as such. But yes, we have different ways to find out the mole of a substance. It is time to look at the 7 pieces of Lego once again. I mean, revise the 7 fundamental units once again. We have the first physical quantity, length. The SI unit is meter and the symbol is small m. The second one is mass. The SI unit is kilogram. The symbol is small k, small g. The third quantity is time. The SI unit is second and the symbol is small s. The fourth fundamental quantity is temperature. The SI unit is Kelvin, which is represented by capital K. The fifth fundamental quantity is electric current. The SI unit is ampere and the symbol is capital A. The sixth fundamental quantity is luminous intensity. The symbol is small c small d and it is for candela. The seventh fundamental quantity is amount of substance. The SI unit is mole, which is having the symbol of small m-o-l. Now, hey, what about the quantities like speed? What is speed? It is nothing but distance per unit time. So we may use length, the first fundamental quantity, and time. Just divide them. So we can say it's a derived unit. The unit of force, acceleration, the density, all of these can be derived from these 7 fundamental units, and that's why the name fundamental. In fact, I would love for you to try figuring out the SI unit of this derived physical quantity, which is density. You may pause the video and give it a shot. Well, density is what? Mass per unit volume, right? Now here is the catch. Volume is length cube. That means the SI unit of volume shall be meter cube. So SI unit of density will be mass. The SI unit is kg. Volume is meter cube. So yep, the SI unit of density shall be kg per meter cube. There you go. Now there is also one interesting unit system that we should know. The CGS system. C stands for centimeter, G for gram, and S for second. This system was widely used before the SI system became the standard. Now that we understand the importance of standardization, let's talk about some more real-world applications of SI units, like in healthcare, where a little dosage change can be fatal, and in sports, wherein a difference of fraction of second can switch medals in Olympics. Also, in engineering and construction, where a little difference in the measurement can lead to the collapse of the entire bridge. And in food industry, where all physical quantities are important, like the mass of ingredients, the cooking time, etc. Not to forget the space exploration, and this we have talked about in depth, how NASA's Mars Climate Orbiter crashed and led to the loss of millions of dollars. Another real-world application can be the climate science, where every small little difference in the measurement of temperature can be very, very crucial. By the way, the real-world applications of SI units are so many that it will take days and days to discuss all of them.